Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all the students. So we are going to continue for chapter 5 in this subject, BHA1113 Engineering Materials, with the topics titled Strengthening Mechanism. And for the chapter objectives, today you should be able to explain and discuss the mechanism for strengthening. As for the lesson objectives, at the end of the semester, students should be able to apply and explain ferrous and non-ferrous alloys microstructure strengthening mechanism and its applications, polymeric and advanced material structure and properties. These are the topic contents for today, which being divided into two. Number one is strengthening mechanism, which includes grain size reduction, solid solution strengthening, and strain hardening. Number two is microstructure, whereby we are going to learn on recovery, recrystallization, as well as grain growth. Okay. Well, metallurgical and materials engineers are often called to design alloys having high strength, yet some ductility and toughness is sacrificed when an alloy is strengthened. Several hardening techniques are at the disposal of an engineer, and frequently alloy selection depends on the capacity of a material to be tailored with the mechanical characteristics required for a particular application. Important to understand of strengthening mechanism is the relation between the motion of large numbers of dislocation. The ability of a metal to plastically deform actually depends on the ability of dislocation to move, because hardness and strength are related to ease with which plastic deformation can be made to occur by reducing the mobility of dislocations. The mechanical strength may be enhanced, that is, greater mechanical forces will be required to initiate plastic deformation. In contrast, the more unconstrained the dislocation motion, the greater is the facility with which a metal may deform, and softer and weaker it becomes. Virtually, all strengthening techniques rely on the simple principle, which is restricting or hindering dislocation motion renders a material harder and stronger. The present discussion is confined to strengthening mechanism for single-phase metal by grain size reduction, solid solution alloying, and strain hardening, as mentioned in the topic content just now. So now let's look at our first topic. The size of grains, or an average grain diameter in polycrystalline metal, influences the mechanical properties. Numbering grain normally have different crystallography orientations, and of course a common grain boundary as indicated in this figure here. During plastic deformation, slip or dislocation motion must take place across this common boundary, say from grain A to grain B over here, from grain A to grain B there. As you can see there, the grain boundary acts as a barrier to dislocation motion for two reasons. Number one, because the two grains are of different orientations, a dislocation passing to grain B will have to change its directions of motion. This becomes more difficult as the crystallography misorientation increases. Number two, the atomic disorder within a grain boundary region will result in discontinuity of slip planes from one grain into the other. It should be mentioned that for high-angle grain boundaries, it may not be the case that dislocation transverse grain boundaries during deformation. Rather, dislocation tend to pile up at grain boundaries. This pile up introduce stress concentrations ahead of their slip planes, which generate new dislocation in the neighboring grains. A fine material is harder and stronger than one that is coarse grain, because the former has a greater total grain boundary area to impede dislocation motion. For many materials, the yield strength varies with grain size according to Hall-Patch equation over here. In this expression, D is the average grain diameter and sigma naught and as well as Ky are constant for a particular material. Note that this equation is not valid for both very large grain and extremely fine grain polycrystalline materials. And if you look at figure 7.15, it actually demonstrates the yield strength dependence on grain size for a brass alloy. Grain size may be regulated by the rate of solidification from the liquid phase and also by plastic deformation followed by an appropriate heat treatment as discussed in previous lecture. It should also be mentioned that grain size reduction improves not only strength but also the toughness of many alloys. Small angle grain boundaries are not effective in interfering with the slip process because of the slight crystallographic misalignment across the boundary. On the other hand, twin boundaries will effectively block slip and increase the strength of the material. Boundaries between two different phases are also impediments to movement of dislocations that is important in strengthening of more complex alloys. The sizes and shapes of the constituent phases significantly affect the mechanical properties of multi-phase alloys. Another technique to strengthen the hardened metal is alloying with impurity atoms that go into either substitutional or interstitial solid solution. Accordingly, this is called solid solution strengthening. High purity metals are almost always softer and weaker than alloys composed of the same base metal. Increasing the concentration of the impurity results in an attendant increase in tensile and yield strength as indicated in this figure. This one figure for copper, for nickel in copper. Alloys are stronger than pure metals because impurity atoms that go into solid solution ordinarily impose lattice strains on the surrounding host atom. Lattice strain fill interactions between this location and these impurity atoms result, and consequently dislocation movement is restricted. For example, an impurity atom that is smaller than a host atom for which it substitutes exert tensile stress on the surrounding crystal lattice, as illustrated in figure 7.17a there. Conversely, a larger substitutional atom imposes compressive strains in its vicinity as shown in figure 7.18a there. These solute atoms tend to diffuse to and segregate around these locations in a way so as to reduce the overall strain energy, that is to cancel some of the strain in the lattice surrounding this location. To achieve this, a smaller impurity atom is located where its tensile strain will partially nullify some of the dislocation compressive strain. For the edge dislocation in figure 7.17b, this would be adjacent to the dislocation line and above the slip plane. A larger impurity atom will be situated as in figure 7.18b there. The resistance to slip is greater when impurity atoms are present because the overall lattice strain must increase if a dislocation is torn away from them. Furthermore, The same lattice-strain interactions shown in these two figures here will exist between impurity atoms and dislocation that are in motion during plastic deformation. Thus, greater stress is necessary to first initiate and then continue plastic deformation for solid solution alloys as opposed to pure metals. This is evidenced by enhancement of strength and hardness. Next is on strength hardening. Strength hardening is the phenomenon whereby a ductile metal becomes harder and stronger as it is plastically deformed. Sometimes it is also called as work hardening, or because the temperature at which deformation takes place is cold relative to the absolute melting temperature for the metal cold working. Most metal strain harden at room temperature. It is sometimes convenient to express the degree of plastic deformation as percent cold work rather than as strain. And the percentage of cold work is defined as follows, whereby A0 is the original area of the cross section that experiences deformation, and AD is the area after the deformation. Strength hardening is often utilized commercially to enhance mechanical properties. Mechanical properties of metals during fabrication procedures. The effects of strain hardening may be removed by an annealing heat treatment as discussed in previous lecture. The figure over here shows the common forming operations which can be found in the market, and the detailed process of this forming operation you might be learning in manufacturing process, which is in other subjects. So in summary, for topic A just now, we have discussed the three mechanisms that may be used to strengthen and harden single-phase metal alloys, which is through strengthening by grain size reduction, solid solution strengthening, and strain hardening. Of course, they may be used in conjunction with one another. For example, in solid solution strengthen may also be strain hardened. It should be also noted that the strengthening effects due to grain size reduction and strain hardening can be eliminated or at least reduced by an elevated temperature heat treatment. On contrary, solid solution strengthening is unaffected by heat treatment. So moving on to our next content for this topic for today is recovery, crystallization, and grain growth under the microstructure. As outlined earlier in this lecture, plastic deforming a polycrystalline specimen at temperatures that are low relative to its absolute melting temperature produces microstructural and property changes that includes a change in grain shape, strain hardening, and increase in dislocation density. Some fraction of the energy expended in deformation is stored in the metal as strain energy, which is associated with tensile, compressive, and shear zone around newly created dislocations. Furthermore, other properties such as electrical conductivity and corrosion resistance may be modified as a consequence of plastic deformation. These properties or structures may revert back to pre-cold work states by appropriate heat treatment, or sometimes called as an annealing treatment. Okay, sometimes called as annealing treatment. Such restorations result from two different processes that occur at elevated temperatures, such as recovery and recrystallization, which may be followed by grain growth. During recovery, some of the stored internal strain energy is relieved by virtue of dislocation motion as a result of enhanced atomic diffusion at elevated temperature. there is some reduction in this number of dislocations, and dislocation configurations are produced having low strain energies. In addition, physical properties such as electrical and thermal conductivities are recovered to their pre-cold work states. Next is on the recrystallization. After recovery is complete, the grains are still in relatively high strain energy state. Recrystallization is the formation of a new set of strain-free and equiax that have low dislocation densities and are characteristic of the pre-cold work condition. Equiax grains are referring to the grains that having approximately equal dimensions in all directions. Yeah. The driving force to produce this new grain structure is the difference in internal energy between the strained and unstrained material. The new grains form as a very small nuclei and grow until they completely consume the parent material, processes that involve short-range diffusion. Those recrystallization of cold work metals may be used to refine the grain structure. As also during recrystallization, the mechanical properties that were changed as a result of cold work are restored to their pre-cold work values. That is, the metal becomes softer and weaker, yet more ductile. Some heat treatments are designed to allow crystallization to occur with this modification in mechanical characteristic. Recrystallization is a process, the extent of which depends on both temperature and time. The degree of recrystallization increases with time, and the influence of temperature, as demonstrated in this figure here, which plots tensile strength and ductility of brass alloys as a function of temperature and for a constant heat treatment for 1 hour. The grain structures found at various stages of the processes are also presented schematically in this figure. The crystallization behavior of a particular metal alloy is sometimes specified in terms of recrystallization temperature. The temperature for which recrystallization reaches completion in 1 hour. Thus, the recrystallization temperature for the brass alloy from this figure is about 140 degrees C. At this point, typically it is between 1/3 and 1/2 of the absolute melting temperature of a alloy or metal, and depends on several factors, includes amount of prior cold work and purity of the alloy itself. Increasing the percentage of cold work enhances the rate of recrystallization, with the result that the recrystallization temperature is lowered and approaches a constant or limiting values at high deformations. Furthermore, it is this limiting or minimum recrystallization temperature that is normally specified in the literature. There exists some critical degree of cold work below which recrystallization cannot be made to occur. Normally, that is between 2% and 20% of cold work. Recrystallization proceeds more rapidly in pure metal than in an alloy. During recrystallization, grain boundary motion occurs as the new grain nuclei form and then it will grow. It is believed that impurity atoms preferentially segregate at and interact with these recrystallized grain boundaries so as to diminish their mobilities. This results in a decrease of the recrystallization rate and raises the recrystallization temperature, sometimes quite substantially. For pure metals, the recrystallization temperature is normally 0.4 melting temperature, where the melting temperature is the absolute melting temperature. For some commercial alloys, it may run as high as 0.7 melting, 0.7 is absolute melting temperature. After recrystallization is complete, the strain-free grains will continue to grow if the metal specimen is left at the elevated temperature. This phenomenon is called as grain growth. While grain growth does not need to be preceded by recovery and recrystallization, it may occur in all polycrystalline materials, metals, and ceramics alike. As a grain increase in size, the total boundary area decreases, yielding an attendant reduction in the total energy that is the driving force for grain growth. Grain growth occurs by the mitigation of grain boundaries. Obviously, not all grains are enlarged, but large ones grow at the expense of small ones that shrink. The average grain size increases with time, and at any particular instant, there will exist a range of grain sizes. Boundary motion is just the short range diffusion of atoms from one side of the boundary to the other. The directions of boundary movement and atomic motions are opposite to each other. So that would be all for today's lecture. And thank you very much for your kind attention and time. I think this will be all for chapter 5, and soon in the next class, we are going to look at on the new chapter, which is chapter 6. So I do hope that everybody understand what is being delivered by today's lecture. And if you do have any question related to the topic, please you may ask me in a group or in Google Classroom, and I'll come back to you as soon as possible. So that will be all for today's lecture, and thank you very much for your kind attention and time, and see you. Bye bye.